Sorry. So this is what I'm going to talk about, the interaction of a turbulent atmosphere and a turbulent ocean. So there is a picture which is a little bit more scientific, and what you see is the different processes which are actually happening at the ARC interface. And they're all important, but I'm only talking today about this. So I'm talking about this shear forces between the moving atmosphere and the moving ocean in a very simple model, neglecting all the other important processes for the moment. And so I actually have this a copy of this painting hanging in my office. And when I hung it up, I didn't really know which way around to hang it up, because if you turn it around, it looks like ARC interaction 2. And this is because just the painter painted in such a way that if you're at the right distance from the ocean surface, then they both look the same. And this probably means that there is not too much difference between the ocean and the atmosphere. And so this gave me the idea that probably the interaction can be described by, or there's a similitude to Brownian motion. And this is what you see here. You see, we have already seen this today on occasions. You see the Brownian particle, which is hidden by the small molecules, and then what it does a kind of a random walk. So this was discovered or described by Albert Einstein in 1905, where he actually found out that, or he used that this Brownian particle is living in two worlds. It's living in a macroscopic world, and so it's just a sphere which is moving in a fluid, and so it's subject to the Stokes law, which is given on the first line over here. And then it also living in the microscopic world, so like a molecule, it's hitting with the other molecules, and so it makes a random walk. And Albert Einstein used these two worlds to actually come up with this formula and then calculate this number here, which is the Avogadro number. So he could obtain this number from observations from the diffusion coefficient. This was later done by Jean Perrin, who later got the Nobel Prize for this work and founded the CNRS. Some years later, there was Langevin, who said, well, all the calculations which were done by Mr. Einstein, I can do it much simpler by just writing down this, what's called today the Langevin equation. And he said, I can just do it in 4 lines. And again, you have here the Stokes law, so the macroscopic world dissipation and this microscopic world forcing, the random forcing, which is given here. But this equation actually took a long time to give a meaning to this equation, to using Ito calculus. So now what I'm going to do is I'm going just to look the same thing, the same problem for the wind. Here we have the wind, and here we have the currents. And if you look at the acceleration of the ocean currents in a simple model, we have a layer of wind and we have a layer of the ocean, and you write down the equation, then the acceleration of the ocean depends on the difference in the difference between the two velocities, the ocean velocity and the atmospheric velocity, and there's just one parameter in this linear version, which is the friction time. Okay, so I took this model, and well, most important, of course, is that this is just a Langevin equation. So you have the slow-moving ocean, which is subject to some dissipation, and then you have an accelerating force here, which is due to the atmosphere. And of course, the atmosphere is moving much faster than the ocean. So we have a classical Langevin equation with a separation in time. And the model actually is not very, for different reasons, which I don't explain today, it's not appropriate. So you have to go a little bit further. You have to actually construct a model where you have an atmospheric layer, an ocean current, and the atmospheric layer, which is forced above by some kind of random forcing. And if you look at this very simple model, so you just have a variable for the atmospheric wind, you have a variable for the ocean current, and you have some forcing above. And the only few parameters you have is the mass ratio between the ocean layer and the atmospheric layer above. So it's called M, it's a very it's a large number, typically order 100. And then you can have, in the nonlinear version, you would have a CD, which is a friction coefficient given here. In the linear version, you would have friction time S, which as was mentioned before. So today, I'm just focusing on one thing of this model, which is the power input. So this is the power the atmosphere injects into the ocean. And to find out, so the power input is just you just have the wind at 10 meters. Usually it's measured at 10 meters above the ocean surface. You have the ocean velocity, and you have the shear between the two. And to calculate the power input here, P, you just multiply the shear times the ocean velocity. The shear here in the linear version would be S times the difference between the atmospheric wind and the ocean velocity. And S is a constant, but you can also use this coefficient, the CD coefficient, when you have instead of S, you can use a CD times the difference between the velocities. So you have a quadratic friction law, which actually doesn't change much in the calculation, in the results. And so what I'm going to look now is I'm going to look at this power injected into the ocean averaged over different times, and then divided by the average power over the average is taken over all the data which I have. So what I want to see is if you have the axis of time, then here you have the variable c actually, and so it has an average value of 1, and then it fluctuates, and sometimes, well, you have also negative events here. So this actually happens when, for example, the wind and the ocean go in different directions. Then of course the wind takes energy or power takes energy out of the ocean. And so this is a variable which has an average which is 1, so it's positive, but it also has fluctuations and goes to the negative. So these is what I'm looking at in this very simple model. And what I'm actually looking at is what's called the fluctuation theorem. So fluctuation theorems were very much considered in the last 10 or 15 years. And they come from non-equilibrium statistical mechanics. So they come from the fact that if you have a hot body and you have a cold body and you have a thermal connection and thermal bridge between the two, then the second law of thermodynamics actually tells us that the heat goes from the warm to the cold. However, when this is these are very small objects, then we can observe that there are these violations of the second law of thermodynamics, and sometimes the energy just goes the other way. So on average, of course, the second law of thermodynamics is correct, but we can have exceptions saying that the second law of thermodynamics is just a statistic law, so it's okay on average, but not at very instant of time. And so this fluctuation theorem, to consider this fluctuation theorem, I have to plot the PDF, the probability density function of this variable c, and this is what you see below here. You see this probability density function, which is given here is this line here, the broadest, the black line here, actually this which is the broadest line here. And then I also look at the probability function of averages. So let's say you do averages over different times. So you take an average here, take an average here, here, and here, and then you see the average fluctuates, but it has less and less chance to actually have negative values or extreme values, and especially negative values. And so the PDF is given here, and the PDF of the PDF's log plot is given here. So this is the black line, and then the other lines are just averages over different intervals, increasing intervals of time. Sorry, this is the instantaneous, and these are the averages, where averaging times go faster and longer and longer here, with longer and longer average times. So the PDF becomes more and more peaked in time. And so now what does say this fluctuation theorem? Well, in the fluctuation theorem, we look at this function the PDF of C. And so if I draw a PDF here, so the PDF looks something like this. And so what the fluctuation theorem says, that I look at a value of, I take a value which is maybe C here, and take a value minus C, and then I look at the value of the PDF at minus C, and I look at the value of the PDF at plus C, and then I divide one by the other, take the logarithm, and I do this for different averaging time, tau. And so here I have a tau. So if tau is of course, if I have longer tau, then this is more peaked around the average or near the average value. And I have PDFs which look like this. And then the fluctuation theorem tells us that if it applies, then the symmetry function should be a linear function of tau in C, with sigma, which is just a constant, which is called the contraction rate. And if I look at my data in my very simple model, it looks a perfect straight line. So here I have the symmetry function here, S of tau, which is divided by tau. So this should be just a straight line if the fluctuation theorem applies, where the slope is given by sigma. And this is verified for this in this very, very simple model. So the project is now to look at this for more and more complex models and see if it stays. But recently I thought, well, maybe first look at real data and see if I find this in real data, because it's no use in looking at more and more complex models if finally in the data it does not apply. So I went to 3 months to another laboratory where people are specialized in satellite observation, satellite data, and I looked at real data. I haven't done much looking at real data before, and I got a little bit discouraged, and then I came about a book, the book of Johannes Kepler. This is one of the books of Johannes Kepler on stellar nova, on supernova. And what he put on the first page of this book is this picture here, which I want to say. So it's a hen which is standing on dung, and what he wrote below it in Latin is grana dat effimo scrutans. So it says she gives, also grana is grain, dat she gives by scrutining the dung. So this is how probably how Kepler felt by looking at all the data he had. So he felt like looking in all this dung and finding grains, or finding gold, finding interesting information. And so this is the same thing I felt by looking at all the satellite data. So I'd like to show this to you. Okay, good. So what I actually did, I took the data, and I had at my disposition, I had data from the wind at 10 meters height observed over the entire ocean, the ocean current at the surface or near the surface, and also the ocean current 15 meters depth. And what I was interested is the power input in the mixed layer, so at around 15 meters depth. So I calculate tau by using the difference between the shear here, which is calculated using the difference between the atmospheric velocity and the ocean velocity, and then multiply it by the ocean current at 50 meters, and this gives me the power. So this is the variable which I consider, and I consider it for 4 regions. So one is in the North Atlantic subtropical gyre here, which is 10 degrees to 13 degrees north, and then in the extension of the Gulf Stream. And I do the same thing for the Pacific to see if there is some symmetry. So Kuroshige extension and subtropical gyre in the Pacific. And the data which I have here, this is for the subtropical gyre in the North Atlantic. What you see is I have data for every 6 hours at a resolution of ½ a degree for 24 years, and it's every 6 hours. And so here you see the PDFs, so the instantaneous values is black curves, then averaged over 500 500 realizations, or 125 days, and then the double, and then 1,500, 2,500, and so on until 5,000 realizations. And so one important remark is that the PDFs are non-Gaussian. They don't look Gaussian. With increasing time, of course, the negative events become less and less likely. And now here I plot again the symmetry function divided by this variable tau, this averaging variable, and we see that all this converges to a straight, almost perfect straight line. So it seems to apply. However, for the Gulf Stream, and this is same for the subtropical gyre, here we have also a convergence on a line which is looking goes to straight line. If you increase the averaging time tau, so tau increases from here down to here. And however, if you look at the extension of the Gulf Stream and the extension of the Pacific, it works less well. So you have it all converges to the same line, meaning that there is a large deviation principle, and this is depending on the rate. This is depending on the rate function which exists, but it's not a straight line. So the symmetry function is not linear with C, and so that means that there is no fluctuation theorem which applies. The same is true for the Conférencier extension. You have a change of slope, which is very conspicuous. And so if you do the same thing again, this is the picture on the left which I've already shown for my very simple model where everything goes on a straight line. And here I used some damping in the ocean, so there is some internal damping in the ocean. And then you also see that these lines, they converge, but actually they converge to a curved line, which is this is here. This is the curved line. So I have a large deviation principle, but I do not have a fluctuation theorem. So probably the reason why it does not work, this fluctuation theorem is not applied directly, cannot be applied directly to the extension of western boundary currents, is because there's energy cascade, and energy is going is not energy is not the main of the energy is not to local interactions of ARC, but is provided from outside, and then there is damping, and so this can be understood by using just a simple model. So these are my conclusions. So the observation suggests that FT holds in some areas of the ocean. So then why do I look at this? Because in non-equilibrium thermodynamics, of course, we do not have anything like the Boltzmann distributions, or a distribution from which all the other properties of the system derive. But if we know that for some of them a fluctuation theorem applies, then we know that there is a large constraint on the probability density functions of these problems, and this can help to then for our investigations. And then fluctuation theorems in this context are, of course, a powerful tool in up and down scaling in the time. And what I want to emphasize is actually that these very simple models analytic models are we can actually calculate things with them, and they help then to understand here the observations, and guide our understanding. But in fact, what's still missing for the moment is to connect the simple tools in a consistent hierarchy to the observations. But I actually find already the same behavior in the very simple models and the observations. So we'll see how the hierarchy behaves. Okay, good. Thank you very much. And if you have questions.
Thank you very much, Achim. We're a little bit late, so maybe as there may be a few questions, can I ask the next speaker to come and prepare the presentation, and that gives us a bit of time to exchange questions if there are any. Yeah, one at the back.
You mentioned non-equilibrium statistical mechanics. do you use in any, do you think Jarzynski's equality has any role in what you've looked at so far?
Yes, I think so. There are different forms of fluctuation theorem. So what I looked today is a detailed fluctuation theorem of Galavotti and Cohen. I haven't looked at other fluctuation theorems as you just mentioned. So if you look at these other fluctuation theorems, the difficulty is you have to kind of define KBT, so the Boltzmann constant, you have to know. So this has been done in experiments, but it's there's a kind of arbitrariness in defining this. And though there's no arbitrariness, there's no free parameter in what I presented. So this is why I looked first at this kind of fluctuation theorems, and I will look at the other fluctuation theorems when I'm really clear to have found some kind of equivalent to the Boltzmann constant for this kind of flows or so. Okay, thank you.